We're talking about a person that is really engaged and passionate about his work. His name is Simon Scholtz. Give him a warm applause. Simon!
Good afternoon, everyone. My name is Simon Scholtz. I'm a mechanical engineering student at the University of Pretoria, South Africa, and also a recipient of the what we call the UP Derek Gray Award. This was awarded at the Eskom Expo for Young Scientists. So, have any of you ever had the idea of generating electricity using speed bumps? Well, today I'd like to present to you my project on exactly that, renewable energy from speed bumps. So the idea is to employ the global network of speed bumps and to generate electricity using these speed bumps. And for this, I designed a unit that can be installed in any speed bump without altering the speed bump's profile or its original purpose. And so I often get the question, how did I get this idea? So we were on a family holiday in one of our coastal cities in South Africa called Jeffreys Bay, which it's pretty warm there now during this time of year. And the place where we were staying had a problem where people were speeding down the access road to the place where we were staying. And then to address this problem, the body corporate decided to install a series of speed bumps. But the problem is these speed bumps were custom made and they weren't made up to standard. And they turned out to be quite uncomfortable to cross. And so after the so manyth time crossing these speed bumps, I was driving with my dad. Comments from him made me realize just how energy inefficient the speed bump is. And so this got me thinking of a way to increase the energy inefficiency of the speed bump. Now, just a little bit of background on the speed bump. The speed bump was invented in 1953 by Arthur Compton, a Nobel Prize winner in physics. But it wasn't until the year of 1983 that his design was implemented on the UK public roads. And then in 2019, the UK reported that the total number of speed bumps have exceeded 42,000. And so today, worldwide speed bumps are a common traffic calming measure. If you look at the energy inefficiency of the speed bump, a vehicle would typically slow down from 60 to 7.5 kilometers an hour in order to cross a speed bump. And that is 136 kilojoules of energy that's being wasted. But unfortunately, the speed bump is not going anywhere. The UK even reported that the total number of speed bumps have increased by 5% in the last 3 years. And so, as I stated earlier, the aim of my research was then to present a new device, which I call the Modular Unit, that can be inserted into any speed bump and enable that speed bump to generate electricity. Now, the Modular Unit, the aim was that the Modular Unit must be easy to install, and it must not interfere with the speed bump's profile or its original purpose. To achieve the aim of my research, the objective was to test different Modular Unit designs and to gauge their potential for real-world use. And so the Modular Unit is only one component of a much larger renewable energy speed bump system. And it works as follows. The vehicle approaches the speed bump at a speed somewhat higher than 7.5 kilometers an hour. The vehicle then crosses the speed bump and depresses the actuator as it crosses the speed bump. Kinetic energy is then transferred from the wheel of the vehicle to the actuator of the Modular Unit. Inside the Modular Unit, the linear motion of the actuator is then converted to rotational motion, which is then delivered at high RPM to a set of dynamos via a gearbox. The stored electricity is then stored, the generated electricity is then stored in the middle of the speed bump. And the idea is to then power access booms, traffic lights, and traffic signs. And so during my research, 3 Modular Unit designs were realized. The first of these designs I did during high school as a high school project, and it used 3 handheld Dynamo Torches. The power output of this unit is 2.25 watt at an efficiency of 16.88%. This unit requires an actuation force of 29 Newton at an acceleration of 1 g. And then for the second unit, I tried to make the dynamos myself using enamel copper wire and donut-shaped magnets. This unit produced a very disappointing power output of 25 milliwatt at an efficiency of 0.12%. The unit also required an actuation force of 98.1 Newton at an acceleration of 1 g. I suspect that the poor performance of the unit was due to short circuits in the windings of the coils, and then also stiff mechanical members which made it difficult to operate the mechanism. For the third mechanism, which is the last mechanism that I designed, it uses 4 stepper motors and produces a power output of 63 watt at an efficiency of 58.9%. This unit requires an actuation force of 72.6 Newton at an acceleration of 1 g. And so I took the best performing modular unit design, which is prototype number 3, and I cut a slotted hole into a commercially supplied speed bump unit. And I then had a vehicle drive over it, and I observed the result. So what I observed was a power output very close to the controlled force testing of 63 watt, and for one wheel that is 18.9 joule. For one axle, which is 2 wheels, 2 modular units, that is 37.8 joules. So in conclusion, the modular unit was tested and found to be a feasible way of reducing the energy inefficiency of the speed bump. I found that the modular unit was easy to install and it generated enough electricity for this research purpose. In my opinion, the modular unit merits further research and development to turn it then into a commercially viable device. Thank you.
One more applause. Thank you so much, Simon. Yeah, that was the last presentation for today. So good work, audience, as well.